We're very happy today to welcome to the IOA Dr. Martin Lamming from the US Naval Research Laboratory. He was born and raised here in Cambridge and did his PhD at the University of Oxford in atomic physics. And from then he was awarded the Lindemann Fellowship, which he took up in the other Cambridge in Massachusetts at Harvard. And then he realized that he actually really liked living and working in the US. So when he was offered a position at the Naval Research Laboratory, he took that, and that's where he's still based. He told me that he has collaborators and has been many times to Dant across the street, but this is his first visit to the IOA. So I hope you'll join me in welcoming him to the IOA, where today he's going to tell us how the supernova Cassiopeia A exploded. Thank you very much.
Okay, thank you. So thank you for inviting me. Thank you to the Kavli Institute for the support for the visit. Thank you to Giulio Delzana for helping me navigate the various bureaucracies involved. In case you're wondering, this picture is an admittedly romanticized view of the Naval Research Laboratory, which is these three lights here, viewed from the Virginia side of the Potomac River. We try to compete with the backs, but we fail. So I'm going to talk about what is, for me, is something of a part-time project. How did Cassiopeia A explode? My involvement is based largely on these two papers, one with Un Huang, published in 2012, which analyzes X-ray data from Chandra, and one with Tea Tamim, which analyzes infrared data taken with Spitzer. So the approach is to understand element and isotopic abundances by spectroscopy and atomic and nuclear physics. This is subjects that I've been talking to Giulio about for the last couple of weeks, albeit in a different context. So element abundances are a key part of what we do. There is an antecedent at the Naval Research Laboratory for this type of work. The person who founded the Space Science Division, Herbert Friedman, here he is, detected in rainwater radioactive isotopes as a result of the Russian nuclear explosion on August 29th, 1949. So this is Semipalatinsk nuclear range. This is the explosion in Kazakhstan. The isotopes meant that they had a very precise idea, very precise confirmation that the Russian bomb had been a copy of Fat Man dropped on Nagasaki, and this started the Red Scare in Washington. Unfortunately, this story didn't make it into the Oppenheimer movie that won all the Oscars at the weekend. I think NRL Public Affairs have slipped up a little bit there, so I'm trying to help them. But this is an important sort of antecedent, and we're going to try similar techniques for supernova remnants using infrared, X-ray, and gamma ray spectroscopy. So the outline of the talk, I'm going to begin with an introduction to Cassiopeia A, just a general features, what it is, why we're interested in it, and then going to discuss the highlights, the Chandra X-ray analysis, the Chandra X-ray observation analysis. Here I'm showing most of the 300 million photons that were detected in the million-second Chandra observation of Cass A that happened in 2004. You can see in green, the continuum is mainly synchrotron radiation. You're seeing the outer shock. Red is silicon, or silicon and associated elements. You're seeing a jet here, and the ring of ejecta. Blue is iron, and here the iron is outside the silicon. That's a real effect. There's an overturn. It's not just projection. And then this yellow dot is the compact central object. And if you look closely, you can see it doesn't align with the center of the jet, which is also going to be interesting. Here is the Spitzer image. This is going to come up in the third part of the talk. And you're seeing oxygen 4. You're seeing the ejecta ring, and there's roughly nothing in the middle. That's not quite true. There is ejecta in the middle, but it just doesn't emit because it's too cold. So we're going to be analyzing this, and then there'll be a wrap-up at the end. Okay, Cassiopeia A, not seen by John Flamsteed on August 26, 1680. Now established that there is unusually for him an error in his catalogue. There is a possible sighting by Cassini, 1671. This is Cassini cited in the third person, people talking about him, and you can read the French if you like, but they're saying that he's seen stars where there wasn't any before in Cassiopeia. Cassiopeia was a part of the sky that was regularly surveyed at this time because this is where Tycho's supernova had appeared. And if you were looking for interesting events in the sky, they thought this would be a good place to look. This is still waiting on classifying of archives in the Paris Observatory. It's interesting that Cassini himself seems to have been a rather careful person, didn't splash into print when he thought he discovered something, because he could afford to be that way because he was funded by Louis XIV. 1671 is an important date. So what makes Cassiopeia A so interesting? Well, it is formerly the second youngest galactic core collapse remnant, and by contrast, it's also one of the most evolved, which makes it particularly interesting. It's well studied at all energies. There are light echoes, optical knots, a compact central object with a natal kick. Here are the light echoes. This is from Armin Rest. Up here, you're seeing all of his data for the Cassiopeia region. Here, you're seeing an average of various clumps of light echoes. So there are 6 broad light echoes that point towards Cass A here. There are, I think, 3 or 4 that point towards Tycho sitting here. There is nothing for the other historical supernova remnant in the field, SN 1181. My guess would be the light echoes from this star would have arrived sometime in the 16th or 17th century, to judge by what we're seeing here. The motion of the light echoes tells you where the echo has come from. And here you're seeing a spectrum of the light echo. This is from Krause et al. And looks very similar to SN 1993J. So this is already a big step forward in understanding what we're looking at. Cass A is a very similar explosion to 1993J, which was a stripped core collapse supernova. Okay, the optical knots, the second interesting thing that marks it out. This is from a conference presentation by Robert Faison. It's also published many times. There are about 2,000 optical knots that are flying out from the center of the explosion, and as they hit the reverse shock, they are heated and live for 50, 60 years typically before decaying away. And if you track their motions back to the center, and because they are over dense, they are not really decelerated by the reverse shock. If you neglect the deceleration and track them back to the center, you find an earliest possible explosion date of 1671. So maybe there's something in the Cassini observation. These optical knots really are, I think, the key to having a very precise knowledge of Cassiopeia A and its parameters. This red arrow shows you the motion of the compact central object, which is almost at right angles to what we consider to be a jet axis. So you can see that there are faster moving optical knots here and here, and this we take to assume to be an axis of rotation in the progenitor. I'm not going to say much more about the jet other than it established this axis that the neutron star or compact central object is moving perpendicularly to that axis. Okay. Oh, well, one thing I was going to say, these optical knots seem to be located in the inner ejecta. They don't come from the outside, they come from the inner ejecta. Robert Faison will tell you that this is not your grandfather's supernova remnant. It's getting brighter in the optical as more and more of these knots encounter the reverse shock. We think they are formed by the inflation of nickel, cobalt, iron bubbles early in the explosion that then compress the non-radioactive gas around them. And that's why they will be located in the inner ejecta. This point gets called the explosion center. I think it's more accurate to say that it is the center of expansion of the inner ejecta. But if I say explosion center, you'll know what I mean. Okay, the optical knots allow, if you take the optical knots outside of the jets, you can infer a distance of 3.4 kiloparsecs. This was done quite a long time ago by Jerry Reed and collaborators. Explosion of 1671. The forward shock speed is 5 to 6,000 kilometers per second, radius 2.5 parsecs. You get all these numbers because you have an accurate distance, because you have the optical knots. You can put all this into hydrodynamical models and you get a reverse shock speed of 2450 kilometers per second, a pre-reverse shock ejecta expansion velocity of around 4,000 and a post-reverse shock expansion velocity of 2280. These numbers are going to come back again, so I don't expect you to remember them. I will remind you. And so when you put these numbers into the hydro model, you get about 3 M sun of ejecta. The explosion energy was about 2 by 10 to the 51 ergs. The ejecta often appear in knots. We probably have a 20 to 25 solar mass progenitor, which is down to 4 or 5 solar masses at explosion, probably due to, no, this is due to stellar wind mass loss, probably aided by a binary companion. And next thing, yes, the dense circumstellar medium that results from this wind loss means you have a strong reverse shock. It drives the reverse shock deep into the ejecta, the current epoch, only at 340 years after explosion. So most of the ejecta are emitting X-rays for us to study, and we can be rather precise about where the reverse shock is in the ejecta and all the other parameters. So those of you who know me know that NRL mainly think I should be working on the sun. Well, we have very precise numbers about its parameters. Cas A is a little bit similar. We can start to do, I think, real physics with Cassiopeia A. We're not, it's really starting to discriminate between certain models. And the most important thing is it was the target of a 1 million second Chandra observation in 2004. This came at just the right time for us. My colleague Una Huang and I were working on the early Chandra data of Cassiopeia A, and we were writing papers to say, yes, we need a much longer observation of Cas A, and if you did this, these are the things you could do. And then this proposal opportunity arose. So we were well placed with papers in the AppJ to refer to write this proposal, and it was successful. Okay, so that sort of highlights of, that's the introduction to Cassiopeia A. I hope it's a particularly interesting object for a number of sort of fortuitous circumstances. So that the Chandra X-ray observation analysis, I'm going to give you a brief survey of what we did. Okay, so I'm showing you the same image I showed at the beginning. Here is an image made by Jaco Vink, which has magnesium over silicon, and you're seeing the strong jet structure. Why this particular abundance ratio shows you the jet, we don't really know. That's still to be resolved. We always intended, once we had 1 million seconds exposure on Cas A, to divide it up into small regions and fit individually. Una Huang went ahead and did this. She fitted 4,319 individual ejecta regions with X-spec, and this is determined by a necessary, a small size region to have enough statistics for a good fit, and also not so many regions that we couldn't never finish it. There's a compromise between getting something done and actually finding something new. The intensity in an emission line looks something like this. So you've got some atomic constants, electron density times ion density times volume. The problem we have is that what we want is just the ion density times the volume. We need some measure of the electron density to actually measure masses of elements in the ejecta. And the things we had tried beforehand, we had some rather clever techniques that worked in this region of the remnant, timing ejecta past the shock and studying departures from ionization equilibrium. However, that didn't work globally, so we had to do something different. So what we do is, given the pixel size, the region size on the sky, we define the volume that we're looking at. And this is a bit more complicated than just a simple area to the 3 halves. We have to have a filling factor. This is a jargon from solar physics, where if you have an emitting volume, not all of that volume may be filled with plasma. In the case of the sun, it's because the magnetic field tells you you can't, the magnetic field gives you substructure. In the case of a supernova remnant, it's a little bit different. Here I'm showing you a couple of models to illustrate from Chevalier and Oishi. This is the radial profile of density. Here's the forward shock. Here's the reverse shock. In the case of a supernova remnant expanding into a remnant stellar wind, the ejecta are compressed into a very strong density spike around the contact discontinuity. So bearing in mind that emission goes as density squared, and that this part of the ejecta comprise all the heavy elements, this is what dominates the emission. When you look at something like this, you're not seeing a ball of gas emitting with a complicated integral along the line of sight of different element abundances and different plasma properties. What you are seeing are the front and back of a spherical shell. And this is a major simplification in how we do this analysis. You're seeing the front and back of a spherical shell, and most of that the line emission is coming from heavy elements on top of a Bremsstrahlung background. By contrast, if you had a type 1a supernova remnant expanding into a uniform interstellar medium, you don't get this strong density spike. You do have a complicated line integral along the line of sight. But fortunately, there are ways of dealing with that if that's your interest. So we go ahead and interpret the spectra as being from the front or the back of the remnant, and you can use these equations here to back out the mass of a particular element. The spectra we see come roughly, they do vary quite considerably over the face of the remnant, but there are roughly two basic classes. Here you're seeing what we see most of the time. These are the products of oxygen burning, which produces silicon, and some silicon burning products. So you're seeing iron L shell here, silicon, sulfur, argon, calcium. These are the helium-like and some hydrogen-like ions. And the continuum is dominated probably by oxygen or lighter elements. So Una has called this a silicon-rich ejecta because silicon is the strongest line. However, I think it is really oxygen-rich ejecta because that's what most of the mass is, and that's giving you the Bremsstrahlung background. By contrast, we see things like this in various parts of the remnant. This is very definitely iron-rich ejecta. The continuum comes from iron. All the lines, except for a few here, come from iron. And this is probably gas that was originated very close to the center of the explosion. Probably right on the edge of where the mass cut was. And we'll talk a lot more about this in a few slides' time. But this was, I think, something quite remarkable about the ejecta of Cassiopeia A. So we go ahead and fit Una fitted 4,319 ejecta regions, add up the mass in each region, and add it all up. And we get something like this. Here are this is oxygen or lighter elements, will be 2.55 solar masses. We have mass contributions from all the other elements. We have iron from the silicon burning, and we have iron that's pure. It's denoted alpha because it's from something called alpha-rich freeze-out that I'll get to in a couple of minutes. And so we have in the X-rays 2.84 solar masses of ejecta. And these columns here are the X and Y, because I'm not an astronomer, I work in X and Y rather than right ascension and declination. These are the velocity components in the plane of the sky, and we can plot them. Here is the velocity of the bulk ejecta. It's moving this way. Here is the velocity of the compact central object. And this is the velocity vector of this clump of iron on the east limb. So this is starting to suggest that we have a hydrodynamic compact object kick. We can't really be too quantitative right now at this epoch about it, but if you extrapolate back to the explosion, roughly speaking, this momentum cancels this momentum. The pulsar or neutron stars are moving one direction and the ejecta are moving in the other, which is roughly what you would expect given the sort of instability that's coming up next. This distribution of iron and this central object kick look for all the world like a standing accretion shock instability. So here is a movie I was given by John Blondin. This is the accretion shock here. Material is raining down on a proto-neutron star. The shock is unstable and it oscillates, and I'll play that again. This is basically a spherical supernova will give you non-spherical dynamics because of this instability. This instability grows in dipole and quadrupole components. So this is looking very suggestive that what we've seen is the instability at the center of the supernova, at the core, the standing accretion shock instability. Okay, I want to say a bit more about the pure iron. This is, I think, one of the central topics that we learn from Cassiopeia that we don't see anywhere else. Here I'm showing you the original discovery. This is from the early pre-VLP data. This is Una Huang's first cut at finding pure iron. I remember sitting in my office talking to her about how we should proceed with the analysis, and I suggested to her that we should look for pure iron, and she started rolling her eyes, thinking, no, what's he asking me to do now? But it didn't take her long to find this. Here it is on the southeast limb, the pure iron. We're thinking that this is from a nuclear burning regime called alpha-rich freeze-out. Roughly speaking, you have nuclear statistical equilibrium in a sort of 10 to the 9 degree range, and there the dominant components are nickel-56 and alpha particles. There are a few other minor elements, a few other trace elements that I will come to in a little bit. So that's why it's alpha-rich freeze-out. And the whole point about this is that this plasma cools down quickly. So the triple alpha reaction that would form carbon and then oxygen and lead to all the other elements doesn't get going. So you have alpha particles and nickel-56, but by the time we observe it has decayed to iron-56 to observe in the current day. So Chris Erickson at Los Alamos refitted this, and he's included nickel as well as iron. So this is not nickel-56, it will have the other isotopes of nickel. And here is his fit. Iron is in green, nickel is in this turquoise. And he's finding a supersolar abundance nickel to iron, which suggests, yes, this is alpha-rich freeze-out. It's important to know if it is alpha-rich freeze-out, then it's much clearer evidence that this came from the center of the explosion. Okay, one of the elements that you get in alpha-rich freeze-out that is uniquely produced in alpha-rich freeze-out is titanium-44. So this is an alpha particle element, and titanium-44 decays to scandium-44 and then to calcium-44, emitting two hard X-rays from the scandium nucleus and a gamma ray, MEV gamma ray, from the calcium-44 nucleus. These lines have all been seen now. So these are the initial discoveries, Ayudin et al. 1997 and Vink et al. 2001 with Beppo Sachs. This is Comptel, this is Beppo Sachs. Seeing these lines, and you see the fluxes up there. Integral also saw them. A little bit surprising that this detection is called a detection, but this one is cleaner. This is the calcium gamma rays. This one's a little bit, I don't know. But the scandium X-rays come up really beautifully with NUSTAR. Here you're seeing Greffenstedt et al. 2014. Here are the two scandium lines. And this is really beautiful confirmation that we're seeing these alpha-rich freeze-out exists in Cassiopeia. The nice thing about NUSTAR is it has imaging as well, so you can see where it's coming from. And this is where the puzzles begin. Here is the titanium-44 decay. This is Yakko's silicon to magnesium plot. Here's the titanium-44, so it's right on the other side of where the compact central object is. It's just where we'd expect it, but it is not where we've seen any iron. Something is either separating titanium from the nickel or the iron, or we don't quite understand. Something's wrong with our understanding. Notice there is very little out here where we thought we saw the pure iron in the first place. The thing that started the whole story in the first place. There is rather little titanium-44. And there's a better view of it here. This is a figure made by Brian Greffenstedt. You've got, in brown, you've got iron K emission. In red, you've got the pure, so-called pure iron K. And the titanium-44 is these blue dots. And you can see it's all sitting where the iron isn't, which is something of a surprise. We need to investigate further. This motivates us to study the infrared data. We're going to look for iron in the interior, see if we find iron that coincides with titanium-44. And this is going to require a bit more work. Before I get to that, there are a couple of other things I want to mention. Okay, I've got some summary so far. The accretion shock instability in the slowly rotating case is more inclined to kick perpendicularly to the rotation axis. So that agrees with what we're seeing. It would transition to a kick along the rotation axis if it was a faster rotation. And that's to do with the accretion shock being spherical and becoming distorted from spherical. And the accretion shock can provide the kick that we're seeing, although that's only been simulated for non-rotating cases so far. The iron should recoil opposite to the compact central object. We're not seeing that, but we do see it in titanium and the bulk ejecta. Yes, we need to analyze Spitzer. I haven't mentioned the jets, but they are probably a byproduct of the explosion, and they define the possible rotation axis. Okay, there's one more thing to mention before I move on to the infrared, and this is quite interesting. It's going to be a variant on this nickel 56, cobalt 56, iron 56 decay chain. This idea is usually attributed to Colgate and McKee, 1959, and I'm going to do a bit more work for the NRL Public Affairs Office. It turned out a few years ago that actually someone called Titus Pankey Jr. did this for his PhD in 1962 and sketched what the light curve of a type 1a supernova should look like. Though in 1962 it's still just called a type 1 supernova. Here you're seeing the six-day half-life of nickel 56 and the sort of 77-day half-life of cobalt 56. And of course, he was another of my predecessors at the Naval Research Laboratory, which is a bit of a surprise. Not surprised he was forgotten about. With this idea, I want to look at go back to the pure iron on the southeast limb. And this is a paper by Toshiki Sato et al., published in AppJ 2023. So they've taken A, B, C, and D and plotted the spectra here. These are all the pure iron, or so-called pure iron spectra, and added them up. Now this is not just the VLP observation, this is 1.6 million seconds of Chandra exposure, everything they have in the archive, all added together. They're seeing titanium, there's some chromium and some manganese here. And here it is on a bigger plot. This is calcium, titanium is this one, chromium, manganese, and then this is the iron K. Titanium and chromium we sort of expect in alpha-rich freeze-out. Manganese we don't. Now, I spent a long time, I was referee of this paper twice for 2 different journals. And I spent a long time asking them and probing. They have to be clear that they've got alpha-rich freeze-out ashes, because you can get manganese from the incomplete silicon burning. And we went through a lot of discussion, and I think it's still a little bit speculative, but I think on balance they have found alpha-rich freeze-out. And their interpretation of the manganese is very interesting. What they think is happening is that this is plasma that started off close to the neutron star when the explosion. It was strongly irradiated by neutrinos during the explosion. Nickel 56, which it would have been at the time of the explosion, underwent spallation reactions with neutrinos. So these would be neutral current reactions. Neutrino plus nickel 56 gives you neutrino plus either nickel 55 or cobalt 55 plus proton or neutron. Nickel 55 decays to cobalt 55 decays to iron 55, and iron 55 decays to manganese 55. So you've got to measure from the spectroscopy what the neutrino flux must have been during the explosion. And they find these numbers from their modeling. So this, I think, is really quite exciting. If they have found alpha-rich freeze-out ashes on the southeast limb of Cassiopeia, if they have successfully identified it and isolated it, this is a major step forward in understanding processes at the center of the explosion. And you can see this is going to be important for observatories to come in the future when you have hopefully comparable spatial resolution to Chandra and higher spectral resolution. This is going to be really quite an exciting thing to pursue. Okay, so let's get on to the infrared. Spitzer. And there will be some JWST images to look at, but I don't have much to say about them for the time being. This is Spitzer. So this is the image of Cassiopeia in a variety of spectral lines. The short wavelength end, you're seeing just the reverse shock, exciting the gas. There's nothing in the middle. And the same goes as you move upwards in wavelength. And then when we get to sulfur 3, oxygen 4, sulfur 3 again, the center starts to fill in. This is because at these wavelengths, the excitation potential is low enough that gas at around 100 degrees in the center of the remnant can excite collisionally these fine structure transitions. We believe that iron 2, which is very close to oxygen 4, is not there, just from Doppler analysis. So we've got some idea that there is ejecta in the center and temperature is 100 to 300 degrees. There is no iron that we're seeing anywhere, except in connection with the reverse shock. I've mentioned that the iron and titanium are unlikely to be fractionated by grain formation or anything like that. Some people have suggested a strange quark star could have caused this. I think that, well, if it is a strange quark star at the center of Cassiopeia, we'd all like to be the person that made the final discovery. But I think the realistic answer is that we have naive ideas about nucleosynthesis and alpha-rich freeze-out. There's a far greater range of things that could happen than we have currently modeled or thought about to date. It sounds a bit strange to say it's going to be mundane things like hydrodynamics and nucleosynthesis that are the explanation, not exotic things like strange quark stars. But I think that that's probably the reality. So this is going to be interesting to work out, of course. Now, in converting infrared line intensities into masses, we have the same problem we had with the X-rays. We have we're measuring basically electron density times ion density times volume, and we need ion density times ion mass times volume. We've got to extract either the electron density or the volume to make progress. In the X-rays, of course, we were able to fit many regions and do some statistics and determine the volume based on a theoretical density profile. In the infrared, we have no prospect of doing this. We only have basically one pixel, one region. That we don't have statistics or resolution to divide up into many regions. And so the way we have to proceed is to get the electron density at which the gas is emitting from photoionization recombination calculations. So the way this goes, I'm showing you calculations of photoionization recombination equilibrium for oxygen, silicon, sulfur, argon, and iron. So this is varying with density. This is in atomic mass units per per cc, which is the way I like to work. The gray bar shows you approximately where, if the Cas A ejecta were uniform density inside the reverse shock, this is approximately where you'd be sitting. So if you're seeing oxygen 3 plus, or oxygen 4, you need to be clumped by about an order of magnitude. If you're seeing silicon plus or silicon 2, it's more like 2 orders of magnitude. Same for sulfur. And so we think the ejecta are clumped by, as I said, the action of radioactivity in the inner ejecta. Iron, interestingly, iron 2 is out here. The iron charge state you would expect if the ejecta were not clumped, if the ejecta were uniform, would be iron 8, iron 7 plus, which would sit here. So we use the electron density inferred from these photoionization recombination equilibrium calculations to work out the mass of each element in terms of its emission, observed line emission. And here are, we have, this is the oxygen 4 map I showed at the beginning. The blue boxes show where we have high resolution Spitzer data. And I'll show you what that means in the next slide, that we have low resolution data all over the remnant, but we don't have the whole remnant observed at high resolution. At high resolution, the profile in Spitzer looks like this, and we can identify the various components. Thea has fit them, and she fit them blind, not knowing what velocities we should be looking for, and we can start to interpret them. What we're interested in are this component and this component. So you see that the line of sight velocity is given along here. And if you remember the numbers I gave you for the reverse shock at the beginning of the talk, we can interpret this, this, and this as ejecta that have gone through the reverse shock. So they're either expanding at the post-reverse shock expansion velocity or faster because they are relatively undecelerated. These are excited, these are coming from thermally unstable portions of the reverse shock and are really not much good for abundance analysis. They emit strongly, but they comprise a very small amount of the total mass that's available. This part and this part are the quiescent ejecta sitting in the photoionization recombination equilibrium in the center of the remnant that comprise the mass of unshocked ejecta. So in this case, I've given you the masses of 003 plus here, so it's about 0.027 solar masses and about 0.0076 between these two. We do this analysis for all the lines. So we use this high resolution spectra to calibrate this low resolution spectrum that comes from all over the remnant. And we do this for every line that's available. Here we're showing sulfur 3, which is showing something similar. Here is the reverse shock on one side, reverse shock on the other, and the quiescent ejecta in the middle. And again, with the masses given here. And at the end of it all, we get a table of masses here. So this is the old X-ray table I had earlier in the talk, and then we add whatever we determine from the infrared. Yeah. Notice that in X-rays, relative to oxygen, neon, magnesium, silicon, sulfur are all subsolar, but in the infrared from the inner ejecta, they're all quite supersolar. So we are seeing an abundance gradient within the remnant. And we determine around half a solar mass emission in the infrared. And the model I had would suggest about 0.3. We think this is actually quite good agreement. We allow ourselves a factor of 2 error either way because there are a number of approximations and assumptions that we had to make because the data just don't cover everything we need. But this, I think, supports our hydrodynamic model that the reverse shock is almost all the way through the ejecta. There's a small amount of the ejecta left inside the reverse shock waiting to be shocked. And this number also agrees with analysis of free absorption by Maria Arias, which is reported in Priestley et al. So this is radio observations giving us essentially the same result. So I feel confident that that Cas A is a stripped supernova, few solar masses ejecta, most of that has been shocked. The infrared support that, so I think we're in reasonably good shape. I can't stop the infrared without at least showing you some of the James Webb Space Telescope results. This is an image from this paper, which was accepted earlier this week. I don't really have time to talk about all of the science that goes on with these different images, but it's really spectacular. There's even another light echo here. I do want to point out that P1, P2, P3, and P4 are positions of integral field spectroscopy. We have very high resolution spectra from these positions. They are chosen for different dust components, P1 and P3. P2 is chosen to look at this structure here, which has become known as the green monster. This is something at Fenway Park in Boston. And P4 is chosen for the abundance analysis. It's meant to be the deep drilling to try and find the iron. So here are the four spectra. I want to just talk a little bit more about P4. Here you're seeing P4 blown up. Look, the oxygen 4 has the same structure as we saw in Spitzer, but at higher resolution. We're seeing reverse shock on each side, unshocked ejecta in the middle. Here is the same in sulfur 3. There is no iron here. So we're not really any further forward in locating the iron, but this spectrum has not yet been properly analyzed. As I explained earlier, there are only 24 hours in a day, and the Crab Nebula observed with JWST goes public sooner, so that's what I've been working on most recently. Here is another visualization of the oxygen 4 from P2 and P4. This is showing you in velocity space down the line of sight. We have, in P4, we've identified this part and this part as being ejecta that are in photoionization, recombination, equilibrium, quiescent ejecta. The rest of this is from the reverse shock. And this is another figure from Milosavljevic 24. It's interesting that P2 and P4 are actually quite different in what they show, though they are close together in the remnant. You have to be rather careful. And I suspect what's going to happen is we're going to have to use the integral field spectroscopy from Spitzer to calibrate the filter images and get global abundances that way. We're never going to get spectra of the whole remnant from JWST because the field of view is so small. So now I'm coming towards the end, just to wrap up a little bit. The first thing I want to mention is that where is the iron? This has been the thing we've been looking for all the time. We think that the iron, the basic premise is that the iron is extremely dilute. It's in bubbles that have been inflated by radioactivity. And I make estimates of how much mass and what mass of iron and what the fluxes would be if the iron were in certain charge states. Remember I mentioned that iron 8, iron 7 plus, would be what we would expect to see if the ejecta were at uniform density. So if we filled Cas A with iron 8 at uniform density, you'd have about half a solar mass of iron, and the flux would be quite large. If you look in Spitzer, here is the iron 4 line. You can see the background subtraction has gone awry. We're in negative, and there's a very small peak here. But that would only, if that were real, you'd have 1% of a solar, it's 1% of a solar mass of iron. It's not the 0.5 that I had on the graph. So iron must be more highly ionized than iron 8. You could look for iron 10, iron 11, iron 13, iron 14. Some of these forbidden lines have been seen in other supernova remnants. It's not an impossible ask to go after these, but it might be harder in Cas A than it is, for example, in the LMC remnants that we've observed with, that have been observed with MUSE on the VLT. So we think that iron exists there, but it's so highly ionized that it's not emitting in a line that we are sensitive to at the moment. So a few conclusions. The unshocked ejecta mass is around half a solar mass. Total ejecta is about 3.3. I haven't said anything about dust, but it's likely to be quite a small amount of dust in Cas A. Some people disagree with me. I'll leave them to make that case. No iron is firmly detected in the inner ejecta. Probably most of the volume is filled with low density iron. We don't quite know how much that would be, but it's curious. Most of the iron in X-rays, we see about 0.14 solar masses. That's about the iron you would expect from a supernova like Cas A, and it's all on the outside. The instabilities have transported the inner ejecta to the outer part. There's likely no conflict with the inferred titanium-44 mass. The separation is different. There's probably quite a wide range of variation in titanium to iron mass ratio. The people I talk to at, for example, Los Alamos, Chris Fryer, take this as a challenge. They're not daunted. They don't think there's a problem. They want to try and, they want to do more hydrodynamics and get even more weird and wonderful things from supernova explosions. Iron infrared lines are a priority for JWST, so that's what we're, first thing we do when we start analyzing those data will be to look for those. There will be more coming out. The key innovation, I think, in the infrared, which allowed us to make this progress, is using the photoionization recombination equilibrium to determine the electron density. So that's all of the science. I want to say a few words about collaborators. Many people have worked on Cas A. I do need to acknowledge a few of the closest ones. This is a slide I made for COSPAR when I gave a talk about Cas A in Moscow, in COSPAR in 2014. The Russians liked it. So the first person to acknowledge is Yakov Vink. This is from a few years ago now, but he looks the same, and he's got Tycho on the screen in the back. Una Huang, you've heard mentioned many times. She did all of the fitting, and I wouldn't be here if she hadn't done all this work. She's been a real asset to work with. And here she is. She's on a second career outside of science. And Thea Tamim, who guides me through the infrared. And here she is sitting in front of the ruins of the observatory in Sarajevo. So I'll just leave you with the last few pictures of Cas A for aesthetic appeal and take any questions. Thank you.